If we generalize for a multivariate case now, it means that we have several observation sets. So this is the first observation set. This may be, for example, distance 1, and we have the second observation set. These may be the distance 2, and then etc. until we have the distance distance n. Okay, and these distances have been observed p times. So p here represent the number of observations. So we can compute the mean value for each one of these distances. And here we have the mean value for distance 1, the mean value for distance 2, the mean value for the nth distance, and we can group them in a vector that is now a multivariate sample. This same reasoning can be made for the random variable. So for each one of these distances, they are associated with a PDF, okay, a continuous representation. Okay, so this is what each one, we can think that the observations have been drawn from the population. So if we talk about a random variable is dealing with the population. What we have now, again, will be a vector of a multivariate vector, which would be composed of the elements of the mean values for each one of those. So they would be the expectation of the multivariate random sample. We discussed about multivariate random sample, multivariate random variance. The covariance matrix is going to deal with the variances. So by definition, we can say that the covariance matrix is the expectation of the so-called dyadic product. That's the we have here the product between the difference between the multivariate random sample and multivariate random variable. Okay, we're basically squaring them. Okay, we know that variance, they are squared quantities. Okay, but there are two types of elements in this covariance matrix. We have the variances. The variances, they are related directly with the spread. Okay, we know that again, standard deviation is the square root of the variance. Okay, both are associated with the spread. And so we have the variances. Okay, and the variances, they are the expectation of the difference of the I observation with the I observation with the I mean. So we can think of these as if we put numbers here, this is the first column, and this is the second column, this is the nth column, Now this is the first row, the second row, and the nth row. So the element 1, 1, this is a variance. Element 2, 2 is a variance. The element n, n is a variance. Now the rest is basically we have these. Let me just erase here and get a different color. We have now the off-diagonal elements, and we should realize that these off-diagonal elements are the same. So this matrix is symmetric. Okay, these elements here are the so-called covariances. Covariance. So the covariances, they are the expectation of the product now of different elements. Here we have the difference between Li mu I. Here we have Lj mu j. Okay, so which means these would be, say, 1, 1, these would be 2 and 2. Okay, that's why you're going to write the subscripts as 1, 2, 1, 3, and 1 n, etc. So this is the definition of covariance matrix. And what these values represent, the variances, they represent, so right here, variance II, these is related to spread. And the elements, Ij, they're related to correlation. Okay, they are not correlation, but they deal with correlation. So they're related to correlation. So they say, basically, they're telling us how much the, say, observation I impacts correlation J, or vice versa. Are they tied up together somehow? You see, the observation, we are measuring GNSS, we're getting GNSS observations, and we receive observation at epoch 1, and then we receive observation at epoch 2. Okay, well, let me do get one very closer here. So L2, L3, L4. Okay, so observation L1 and observation L2, they have been observed close together. So the electromagnetic signals have gone through a similar portion of the atmosphere, so they have been affected similarly by troposphere and ionosphere. So we can say that L1 and L2, they are correlated, or they're more correlated than, for example, L1 and L4. Okay, L1 and L4, the electromagnetic distances, whose path is represented here by these straight lines, they have crossed the atmosphere, different portions of the atmosphere. So L1 and L2, they would be more correlated, more correlated than L1 and L4. So we could, even if we write the value here of the covariance, these would be, I don't know, close to 1, and the covariance for this guy here 1 and 4 would be close to 0. So from these characteristic of the covariances, we can compute the correlation. Okay, correlation will be the ratio between the covariance and the product of the standard deviations. And correlation is a quantity that is bound between -1 and +1. So if the correlation coefficient, as we call this guy rho here, equals to 0, we are going to say that there is no correlation. It is easy to see if basically if there is no covariance equals to 0, that will indicate, I mean, if a covariance is very small, we will know already that the correlation will be very small. So correlation rho equals to 0, it indicates that there is no correlation. On the other hand, we may have a correlation approaching 1. Okay, so any positive correlation, okay, goes to the maximum of 1. That would be 100% correlation. So we could think then that these two observations, they're affected by exactly the same systematic effect. Okay, so if whatever is affecting observation 1 is affecting observation 2, and the higher the correlation is, the closer these effects are. And then we have negative correlation, which would indicate that the effect that observation L1 receives is the opposite of correlation of observation L2. Okay, so they are negatively correlated. So there is still a correlation, but it's negative, so it is the opposite. So I used to say that here, if observation L1 is nizis, observation 2 is nizis. Here, if observation 1 is nizis, the other just cuffs. So very interesting and funny diagram showing a correlation. I don't know, and there is no, it's just for fun. But in the 1990s, the TV was very small, large, and the guy was small. And now we have in 2011, when I got this image, is the opposite. So that would be a negative correlation. Let's discuss a concept that is very important, the concept of bias, accuracy, and precision. So let's start. You want to start here, choosing a color. Okay, red. We have 3 observation sets, okay? Observation set L1, observation set L2, observation set L3. Okay, each one of those, of course, will give us different mean values, L1 bar, L2 bar, and L3 bar. These are the sample means. Here we have a population value. So, okay, so this is the expected value of these observations. In this example here, observation called P. So let's use here the mu. Mu is the population mean. We can say that the population mean equals to the mean of the sample. Okay, actually, I'm sorry, sample 3, L3. On the other hand, there is a bias, and the bias is this difference between the mean values. So we have a bias between the values of L2 minus mu, L1 minus mu. Okay. Now, what about precision? Precision and accuracy, they relate with spread. So what we have in here is the spread related to this observation set. Okay. So in this figure, we're using these normal the Gaussian function to represent the frequency distribution. So we have then the observation L3, okay, plus or minus the standard deviation, okay, the standard deviation of the population, sigma mu. What about the spread of these observations L1 and L2? Okay, which one is better? So this guy here, okay, L3 has 0 bias, okay, and it has a certain spread, okay. But what about the other ones? What about L1? Okay, L1 has a spread of plus or minus this quantity here. Okay, this is a spread. Okay, this is the spread related to L1. Okay, so this is sigma plus or minus sigma 1. And what we have in here now is the bias. Okay, so observation L1 is has a smaller spread, smaller standard deviation than observation set L2. So this here is the standard deviation, okay, of L2, okay, plus or minus S2. Okay, so which means that we can say that observation L1 is more precise than observation L2 because S1 is less than S2. Okay. Now, in terms of accuracy, the accuracy relates to how much they are off the mean value plus their spread. Okay, so which means that this is precision and this is accuracy. Accuracy will have to do also the bias. So accuracy includes the bias. So in which case we could say that yeah, well, 1 is also more accurate than L2. If we look only in terms of precision, though, just in terms of precision, okay, so let's put in terms of accuracy. Accuracy, the more accurate is L3, the second more accurate is L1, the third more accurate or the least accurate is L2. Okay, as far as precision goes, precision has to do with internal accuracy, internal spread. Okay, so the standard deviation S1 is less than the standard deviation of S3 and less than standard deviation of S2. So, which means in terms of precision, observations L1 are more precise than observations L3, which are more precise observation L2. Let's look how we can represent that mathematically.